Imagine the fastest thing you can possibly think of. A rocket blasting into space, a lightning bolt flashing across the sky, even a signal racing through the internet. Now multiply that speed millions of times. That's how fast light travels. Light moves at about 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second. It crosses the distance between the Earth and the Moon in barely over a second. It can travel from the Sun to Earth in just 8 minutes. But here's the strange part. No matter how powerful the explosion, no matter how advanced the technology, no matter how much energy you use, nothing in the universe can go faster than light. Not stars, not spacecraft, not even information itself. Why would the universe impose such a rule? Why does nature draw a hard line across motion itself, declaring that beyond this speed nothing can pass? Is it simply a property of light? Or is it something far deeper, written into the fabric of space and time? Tonight, we're going to travel from the smallest particles of physics to the largest structures in the universe, from photons and planets to galaxies and the birth of the cosmos itself. And along the way, we'll uncover why the universe has a cosmic speed limit and how that single rule quietly shapes everything we see. Out in the vast darkness of space, light moves with astonishing speed. It races across the universe at about 300,000 kilometers every second. That's fast enough to circle Earth more than 7 times in a single blink. And yet, strangely enough, even this incredible speed has a limit. It might sound odd at first. After all, the universe seems boundless. Galaxies drift through space, stars explode, planets whirl in silent orbits. In such an immense cosmos, you might expect motion to be unlimited. But nature quietly enforces a rule. Nothing can outrun light. Imagine throwing a ball while standing on a moving train. The ball's speed adds to the train's speed as it flies forward. Common sense suggests the same should happen with light. But strangely, no matter how it's emitted, light never goes faster. Even if a star races through the galaxy at tremendous speed, the light it releases still travels at exactly the same cosmic pace. It doesn't stack speeds like cars merging on a highway. Instead, the universe seems to protect this speed like a sacred boundary. So the question quietly emerges from the darkness of space. Why does the universe impose this ultimate speed limit? What invisible rule locks motion to this precise number? To begin answering that mystery, we first need to see how this speed shows up everywhere in the cosmos. Look up at the night sky, and every point of light tells a story of motion. Photons leave distant stars and begin a journey across unimaginable distances. Some of that light travels for millions or even billions of years before reaching Earth. Yet no matter where it begins, it always moves at the same precise speed. Astronomers have measured this again and again across the universe. Light from exploding supernovae, blazing quasars, and quiet distant stars all behave identically. No matter how powerful the event or how distant the galaxy, the speed never changes. It's as if the entire cosmos runs on the same cosmic clock. Imagine ripples spreading across a calm lake after a stone is dropped. Those ripples move outward at a fixed speed determined by the water itself. In a similar way, light seems to ripple through the fabric of space, and that fabric quietly determines how fast those ripples can travel. Even more surprising, motion doesn't change this rule. A galaxy rushing away from us at incredible speed still sends light that travels normally. A star spinning rapidly or orbiting another star makes no difference either. Every photon obeys the same universal speed limit. This strange consistency hints at something profound. The speed of light isn't just about the light itself. It seems to be woven into the structure of the universe. And to understand why, we have to zoom far deeper, down to the smallest scale of reality. To uncover the deeper reason behind this cosmic speed limit, the journey now shrinks dramatically. Far below the scale of stars and galaxies lies a strange microscopic world. Here, light is no longer just a glow crossing the darkness of space. Instead, it appears as tiny packets of energy called photons. Photons are unusual travelers in the universe. Unlike planets, asteroids, or even atoms, they have no mass at all. Because of that, they can't slow down, rest, or drift along casually. From the moment they are created, they move at the universe's maximum speed. Picture a spinning ice skater pulling in their arms. As the skater tightens inward, the rotation speeds up dramatically. Energy concentrates into motion, becoming faster and faster. Photons behave in a similarly extreme way. pure energy expressed as motion itself. At this scale, light is deeply tied to the laws of electromagnetism. Electric and magnetic fields continuously create and sustain each other as they move. This self-sustaining wave travels through space like a perfectly balanced ripple, and the properties of space itself determine how fast that ripple can go. So the speed of light begins to look less like a coincidence. It's not simply how fast photons move by chance. Instead, it seems written into the basic rules governing energy and fields. And once we zoom back out toward planets and stars, that rule becomes visible everywhere. Now the perspective expands again, moving from the microscopic world back to familiar cosmic scenery. Within our own solar system, the speed of light quietly shapes everything we observe. Even something as ordinary as sunlight carries the imprint of this universal rule. Because when we look at the sun, we're not seeing it exactly as it is now. Light leaving the surface of the sun takes about 8 minutes to reach Earth. That means the sunlight warming the planet right now actually began its journey earlier. Every sunrise, every bright afternoon, every glowing sunset is slightly delayed. In a subtle way, Earth is always looking 8 minutes into the past. Imagine hearing thunder after seeing lightning during a storm. The flash arrives instantly to our eyes, while the sound travels more slowly. In space, light is the fastest messenger, but even it needs time to arrive. Distances between worlds are simply so vast that those moments begin to matter. The same rule applies across the entire solar system. Sunlight takes over 4 hours to reach distant Neptune. Signals sent from spacecraft exploring the outer planets must travel this same cosmic highway. Every message, every image, every discovery is carried by light across enormous distances. So even in our planetary neighborhood, this speed limit shapes reality. It determines how quickly information moves through space. It quietly controls how we observe the universe around us. And soon, scientists would discover that this limit isn't just about light. It's built into space and time themselves. The speed of light might sound like a distant cosmic idea, something that belongs only to stars and galaxies. But surprisingly, it plays a quiet role in everyday life here on Earth. Modern technology depends on understanding exactly how fast light travels. Without it, much of our interconnected world simply wouldn't work. Take the navigation systems guiding cars, airplanes, and ships across the planet. Signals from satellites orbiting high above Earth travel at the speed of light. These signals race down to receivers on the ground in tiny fractions of a second. By measuring those travel times precisely, devices can calculate their exact position. Scientists also use lasers to measure distances across space with incredible accuracy. By sending pulses of light toward distant objects and timing their return, they can calculate distances the same way a bat navigates using echoes. Even the distance to the moon has been measured this way with astonishing precision. Space missions rely on this principle as well. When engineers send commands to spacecraft exploring Mars or beyond, those instructions travel as radio waves, another form of light. Every maneuver, every photo, every signal back to Earth follows this universal speed. So the cosmic speed limit isn't just an abstract rule of physics. It's part of the invisible infrastructure guiding technology and exploration. And yet, as useful as this constant is, scientists eventually realized something even deeper. This speed limit isn't merely about light traveling through space. It's tied to the very structure of space-time itself. In the early 20th century, a remarkable idea reshaped how scientists understood the universe. A young physicist began asking a strange question about light and motion. What would happen if someone tried to chase a beam of light through space? That curiosity led to a revolutionary insight about reality itself. According to Einstein's theory of relativity, the speed of light isn't just a property of light. Instead, it is a built-in feature of space-time, the invisible stage where the universe unfolds. Just as a river's current sets a limit on how fast a boat can move upstream, space-time sets the ultimate pace for anything that carries energy or information. As objects accelerate closer to this cosmic limit, strange effects begin to appear. Time starts to slow down for the moving object compared to everything around it. Distances contract in the direction of motion, almost like space itself compressing. These effects grow stronger the closer something gets to light's speed. Imagine pushing a heavy sled across a snowy field. At first it slides easily, but the faster you push, the harder it becomes to accelerate further. Near the speed of light, this resistance becomes extreme. Adding more energy doesn't increase speed much. It simply increases the object's energy. Eventually, the effort required becomes infinite. No engine, no explosion, no imaginable force can push a massive object beyond that boundary. The universe quietly enforces this rule everywhere. And long before humans discovered it, this same limit was already shaping the birth of star systems like our own. Billions of years ago, long before Earth existed, our solar system was only a vast cloud of gas and dust. Gravity slowly pulled this cloud inward, causing it to swirl like a gigantic cosmic hurricane. At the center of that spinning disk, matter gathered and compressed until a new star ignited. The newborn sun suddenly flooded the surrounding space with powerful radiation. Light from the young sun began racing outward in every direction. Those photons carried enormous energy into the disk of gas and dust surrounding the star. Just like sunlight warming Earth today, this radiation heated and stirred the material nearby. Tiny grains collided, stuck together, and slowly began building larger structures. Imagine dust swirling in a beam of sunlight through a window. Some particles drift freely, while others bump together and clump. In the early solar system, something similar happened on a far grander scale. Light and heat from the sun helped shape how matter gathered into planets. Closer to the sun, intense radiation pushed lighter gases outward. Farther away, cooler regions allowed ice and heavier materials to accumulate. These differences created distinct zones within the forming solar system. Rocky planets formed near the sun, while giant gas worlds grew in the colder outskirts. So even during the birth of planets, light played a powerful role. Its energy traveled across the young solar system, shaping temperature and motion. The speed of that light determined how quickly energy could spread through space, and that same steady flow of sunlight would later become essential for life on one small planet. Here on Earth, the speed of light quietly shapes how life experiences the universe. Every ray of sunlight warming the oceans and forests began its journey minutes earlier. Energy released from the sun travels across the empty space between worlds. Only after that 8-minute voyage does it arrive to illuminate the planet. This steady stream of light powers nearly every system that keeps Earth alive. Plants capture sunlight through photosynthesis, turning light into stored energy. That energy flows through ecosystems, feeding animals and sustaining life. In a sense, every meal on Earth begins with a photon from the sun. But light's finite speed also affects how we observe the universe. When astronomers look through telescopes, they aren't seeing objects as they are now. They are seeing ancient light that has been traveling for years or centuries. Even nearby stars appear as they existed sometime in the past. Imagine watching a distant lightning strike across a wide plain. You see the flash instantly, but the event already happened moments earlier. Across the universe, this delay becomes enormous because distances are so vast. Light turns the night sky into a vast archive of cosmic history, and the farther scientists look, the further back in time they peer. Light from distant regions of space has been traveling for millions of years. Entire galaxies send us messages from the ancient universe. To truly grasp this cosmic time machine, we need to expand our view beyond our solar system. Now the scale expands far beyond our solar system. Our sun is only one star among hundreds of billions inside the Milky Way. Across this enormous galaxy, light constantly travels between stars, clouds of gas, and glowing nebulae. And even here, the cosmic speed limit quietly shapes what we see. The nearest star system beyond the sun is about 4 light-years away. That means its light takes 4 years just to reach Earth. When astronomers look at that star tonight, they're seeing it as it was years ago. In a sense, every star in the sky is a small message from the past. Across the Milky Way, the delays grow much larger. Light from the galaxy's center takes more than 25,000 years to reach us. The glowing nebulae scattered across the galaxy are ancient snapshots. What we observe today actually happened long before human history began. Imagine standing on a mountain watching a distant storm. Lightning flashes across the horizon again and again. But each flash you see actually happened moments earlier in the storm. The universe works in a similar way, just across vastly greater distances, and when telescopes peer beyond our galaxy, the scale becomes even more staggering. Light from other galaxies travels for millions or billions of years. Every observation becomes a window into the universe's distant past. To understand why this is possible, we must look back to the very beginning of cosmic history. To understand the deepest role of light's speed, the journey must travel all the way back to the beginning of the universe. Nearly 14 billion years ago, the cosmos emerged from an extremely hot and dense state. Space itself began expanding, carrying energy and matter outward in every direction. In that newborn universe, light became one of the first great messengers of information. During those early moments, the universe was filled with a blazing sea of radiation. Particles, energy, and light constantly collided in a chaotic cosmic storm. Photons bounced endlessly between particles like pinballs in a crowded machine. Only after hundreds of thousands of years did the universe cool enough for light to travel freely. When that moment arrived, something remarkable happened. Photons suddenly began streaming across space without constant collisions. Those ancient particles of light are still traveling today, filling the universe with a faint glow. Scientists now detect this ancient radiation as the cosmic microwave background. Even in that early universe, the speed of light set a fundamental boundary. It determined how quickly energy and information could spread through space. Regions of the young cosmos could only influence areas within a certain distance. This limit shaped how structures in the universe gradually formed. Galaxies, stars, and cosmic patterns all grew within this framework. The speed of light quietly governed how the young universe evolved. From the first radiation after the Big Bang to the galaxies we see today, this constant has remained one of the deepest rules written into the fabric of reality. When we step back and look at the universe as a whole, the speed of light begins to feel less like a number and more like a boundary written into reality itself. It defines how quickly anything can move, how fast information can travel, and how events can influence one another. Across billions of galaxies and unimaginable distances, this single rule remains unchanged. It is one of the quiet laws that holds the universe together. Imagine the cosmos as an enormous stage where every event sends out ripples. A star explodes, a galaxy collides, a planet forms around a newborn sun. Those ripples travel outward through space, carried by light and energy. But they can never outrun the cosmic limit that space-time itself imposes. Because of this boundary, the universe unfolds like a vast story told across time. Light becomes the messenger carrying chapters of that story across space. Every photon reaching Earth brings news from somewhere far away. In this way, the night sky becomes a library of cosmic history. When humans look upward through telescopes, they are not just observing distant objects. They are witnessing events that happened long before our planet even existed. The speed of light turns the universe into a grand archive of time. Each observation reveals another fragment of the cosmos unfolding, and perhaps that is the most humbling realization of all. Even in a universe filled with unimaginable power and scale, there are limits. Within those limits, galaxies form, stars shine, and life eventually emerges. And somewhere on one small planet, a curious species begins asking why.